Hey, it's Brian again. We're going to be talking about circular motion today. And for circular motion at the level we're going to talk about it, it's basically an extension of the force and motion things we've been doing. And we've been treating situations where we're looking at force and then we look at the accelerations that they cause. And in this case, in dealing with circular motion, the acceleration is just the acceleration of circular motion. When things are going in circles, that means there's an acceleration. And there's an acceleration directed towards the center. Since the acceleration is directed towards the center of the circle, there must be a force directed towards the center of the circle. And this might be the long-range force of gravity, which is something we'll talk about when we talk about gravity. But that's coming later. This is the type of thing we're going to be looking at. So here's a situation with a person throwing a hammer. So we have this hammer on the end of a chain, and the person spins in a circle and gets this hammer up to a really, really high speed and then lets it go. The hammer has a mass of 7.3 kilograms. It's the end of a 1.2 meter long chain. The person can get the hammer up to 29 meters per second. And the question is, what is the tension in the chain? This is the type of problem we'll solve. But before we get there, it's necessary to do some review. Remember, in Chapter 3, we saw that for uniform circular motion, for something moving in a circle at a constant speed, and the speed is related to the period, according to this relationship right here, there's an acceleration directed toward the center of the circle. And the magnitude of the acceleration is just equal to v squared divided by r. And we did some problems using those concepts back in Chapter 3. Well, now we're going to take that concept of circular motion and the acceleration and add forces to the mix. And if I add forces to the mix, I'll say this: since there is an acceleration directed towards the center of the circle, there must be a net force directed towards the circle. And the value of the net force is just equal to m times v squared over r. It's directed towards the center of the circle. So there must be forces directed inward if I have an object moving in a circle. So here's a situation I want you to think about. Suppose there's a car and it's turning a corner. And when a car turns a corner, it's basically following an arc of a circle. And we'll do a bunch of problems like this. Question: what is the direction of the net force acting on the car? I'll give you 15 seconds to think about that, and we'll come back together. And of course you're saying, Brian, you scamp, you just talked about this on the preceding slide. You said if there's an acceleration directed towards the center of the circle, there's a force directed towards the center, where this car is clearly going at a speed v in a circle defined by this blue arrow right here. So as a consequence, if the car is going in a circle, there's an acceleration directed towards the center of the circle. There must be a net force directed towards the center of the circle. So the answer must be E, and in fact you are correct. Now here's a situation I want to look at, and this is a point we're going to come back to later. If this is a woman who's riding a horse, and the horse is going in a circle around the barrel here. So the horse is describing this like circular path. And she's leaning into the turn. And you don't, when you turn a corner on a bicycle or when you turn a corner walking, you lean into the corner to the turn too. Not as much as this, but you definitely lean in. And the reason is there has to be a force directed towards the center. And we've said that the ground forces on you come in two flavors. One is the normal force. One is the friction force. Okay, so the normal force is directed upward, and we know that in fact the normal force, the magnitude, is just going to be equal to the weight force. There has to be a force directed towards the center of the circle for the horse to make this turn, okay, because the horse is going in an arc of a circle like so. There's an acceleration directed towards the center of the circle, therefore there's a net force directed there. And the force in this case is the friction force. And the magnitude of the friction force is just equal to the static friction force. We know that that's true. But now let's think about the forces that the ground is exerting on you. So the ground is exerting a normal force on you and the horse. The ground is exerting a friction force, and the sum of those two forces, so if I take those two vectors and add them up, it makes a vector that points this way. And the horse is going to lean itself so that the force is going to be along the axis of its body, and that is typically true. If you're taking a turn, you're going to lean into the turn so that the total ground force forms a vector that points along the line of your body, and that is important for stability. Okay, I'm going to mention a couple of words right now, and then we're never going to use them ever again. And those words are centrifugal force and centripetal force. There is no centrifugal force. We're going to obliterate that word. There is no centripetal force. Okay, that is not a thing, because there's a force that produces centripetal acceleration. There's a force directed towards the center of the circle, but it has to be one of the forces that you already know and love. Okay, these are so-called pseudo forces. I don't even want to get into what that means, but they aren't real. They aren't real forces. They're just in a moving frame of reference. They're things you experience, but don't worry about it. We do not use that. Something's going in a circle, there's a force. The force is one of the forces that you know and love, such as the weight force, or the normal force, or the static friction force. The force pushing towards the center of the circle has to be one of the forces that we already know and love. But I do want to stop for a moment and talk about feelings. Okay, I want to talk about feelings. Whenever I talk about feelings, I'm thinking about my wife, Carol, and she's a totally lovely woman. And I hope at some point that you will be able to cross paths with her so she can join us for an event on campus or something like that, because I would love for you to meet her, and she would very much love to meet all of you. Now, if you are in an elevator and the elevator is accelerating upward, the normal force is bigger than the weight force. And the normal force is what you experience as your apparent weight, because the apparent weight is just the magnitude of supporting contact forces. And we talked about this at our in-person section. And it's what you feel as weight. It's your qualitative experience of weight, because you do not feel the weight force acting on you. I'm sitting in a chair right now. What I feel is the chair pushing up on you. I feel the normal force. And if the normal force is bigger, the chair is pushing on me harder, I feel heavier. Okay, so we're going to define the apparent weight as just equal to the magnitude of your supporting contact forces, usually, but not always, the normal force. Now let's take a look at a problem here. We have a car going over a hill at a speed of 20 meters per second, and as we'll see, when people who are making roads sculpt hills, they sculpt them in the shape of a circle. It's an arc of a circle. And actually they specify the radius for the circle. And in some parts of the country, specifically West Virginia, I was able to find a thing that said for roads with certain speed limits, you sculpt the hills into a circle which has a radius of at least 60 meters. Okay, so the car is going over the crest of a hill. Do the people in the car at this instant feel heavy or feel light? Now, let's do a strategy. And I want you to think about this. Okay, we're going to strategize. When you're strategizing, you're basically saying, what the heck is going on and what physics am I going to bring to bear? Well, this is a question about feeling heavy or feeling light. This is clearly a question about apparent weight. And if you're in a car, okay, so here's your car seat, and here's you sitting on the seat in the car, the force which is supporting you is the normal force of the seat on you. And so basically, this is a question about the normal force during this moment. Okay, so we're going to look for this normal force and ask, is the normal force bigger than weight? And if the normal force is bigger than the weight force, people will feel heavy. If the normal force is less than the weight force, people will feel light. And that is our strategy. Next piece we're going to prepare. And for preparation, I want to think about this. What's the direction of the net force on the car? Well, the direction of the net force is basically asking us about the acceleration. Well, the car is going through the arc of a circle. The acceleration is directed towards the center of the circle. And so clearly the net force is directed towards the center of the circle. The net force is directed straight down. Okay? That's the direction of the net force. We're going to continue our preparation by drawing a free body diagram. And I do love me a good free body diagram because it really helps you wrap your mind around the problem. Now let's identify the forces acting on the car. And interestingly, there is no force in the forward or the reverse direction. There are no horizontal forces because the car is moving at a constant speed. There's no force making it speed up. There's no force making it slow down. It's just moving at a constant speed. There is no friction force. The car, if it was just sliding on a frictionless surface, it would keep moving at a constant speed. So no horizontal forces, only vertical forces, and there are two. There's a weight force which is acting downward and a normal force which is acting upward. But we know that the net force is directed downward, and so as a consequence, the upward normal force is smaller than the weight force. Okay, we know that that's true. Now, before we continue, let's do this. Let's write down an expression for the apparent weight of the car. So here's the free body diagram again. I've got a weight force which is directed downward. I have a normal force which is directed upward. And we said the normal force is less than the weight force. And since the normal force is less than the weight force, we've already answered the basic question, which is that the people are going to feel light. Okay? And that actually matches with your experience if you've ever done this. You've ever had a brother who drives over things like that way too fast. You've experienced it in a rather dramatic fashion. But anyway, people are going to feel light. The normal force is less than the weight force. But I want to do this. I want to write down an expression for the apparent weight. And that's something which will be useful for us later. Now, let's do this. Let's write down Newton's second law. Let's write down an expression for what the net force is in terms of the magnitude of other forces. Well, if I'm just looking at magnitudes, the net force is pointing downward. So the magnitude of the net force is going to be equal to the magnitude of the weight force, because that's pointing in the direction of the net force. It's working with us, minus the normal force, which is pointing upward. It's pointing opposite us. So the magnitude of the net force is the thing that points in the direction of the net force, minus the thing that points opposite. But the apparent weight, remember, in this case, it's the contact forces supporting you. So the contact forces supporting you in this case are the normal force. So my expression for the apparent weight would be this. The apparent weight is just equal to the normal force. The normal force, if I take that equation that we just wrote and solve it, is going to be equal to the weight force minus the net force. But the net force is equal to m times a. So this is my expression for the apparent weight. And we will use that later. And finally, coming back to this point, do the people in the car feel heavy or feel light? We already answered that. They do, in fact, feel light. Now I want to look at another situation of a car going through an arc of a circle, but it's a much more exciting situation. And this is a video that I will show in class. This is a car going through an upside down loop, and this is kind of a remarkable thing. They have this teeny little compact car going through an upside down loop. My question is this, for starters, what is the direction of the net force on the car at this point? Take 10 seconds to think about it. Well, the acceleration is directed towards the center of the circle. So the net force must also be directed towards the center of the circle. We know that that's true. Now let's continue. What's a free body diagram for this situation look like? And this one's a little bit different. I want you to pause the video for a second and think about what the free body diagram looks like before I talk about it. So pause, think about it, we'll be back. Well, we know there's a downward weight force. And you're tempted to say there's some sort of an upward force, but there isn't an upward force. There's nothing pushing the car up. There's only the things pushing the car downward. The surface of the track can only push the car in that direction. The normal force is actually directed downward in this case, which is kind of crazy to think about, but is absolutely true. So, if we write down an expression for the apparent weight, we're going to start by reminding ourselves what the free body diagram is: downward weight force, downward normal force. The net force, the magnitude of the net force, is just equal to the force of the weight plus the normal force, because they're both pointing in the direction of the net force. So if you sum those two, that gives you the net force, and that's just equal to m times a. Of course, the apparent weight in this case is the normal force. The normal force is equal to m times a minus w. Okay? Now I want you to think about the two examples that we did of the car. And think about the expressions that we have for the apparent weight. In this case, the apparent weight was equal to ma minus w. In the previous case, we had the apparent weight was equal to W minus ma. And take a look at the chapter. In the chapter, you find this equation right here. And this says the apparent weight is equal to W plus ma. Now, that's different than the previous two expressions that we got. So who's right? And the answer is they're all right. This is not a law. There is no apparent weight equation. Okay, there is no apparent weight equation. This is true for the specific case of a person in an elevator accelerating upward and a few other situations. But it is not generally true. This is not a numbered equation. This is not like a rule or something like that. This is just for this particular case, that's the apparent weight. But you can't use this to solve other problems. So do not use this equation. Now let's return to the problem that we started with, which was this problem of the hammer throw. So the person is swinging the hammer at the end of a chain in a circle, gets it moving at a pretty high speed. Question, what is the tension in the chain? We start with the strategy by strategizing. And the strategize step, what I want you to do is I want you to tell me what sort of motion do you have? How are you going to solve this problem? And my strategy in this case is just to say, look, this is a circular motion problem. The person is swinging the hammer in a circle. This is a problem of circular motion. Okay, that's how we start. Next piece, we're going to prepare. And let's start by thinking about the acceleration. Well, we have the hand. I'm going to do a top view. Now for preparation, what I'm going to do is this. I'm going to draw the motion. But for circular motion, it's fairly straightforward. I have an object moving in a circle at a constant speed. The acceleration is directed towards the center. And the magnitude of the acceleration is just given by the expression v squared divided by r. Okay? So in this case, we can actually solve what the acceleration is. It's equal to v squared divided by r. And we have everything we need to be able to do that. So let's go ahead and do it. So we have the thing is moving in a circle, and let's assume the radius of the circle is equal to the length of the chain. So I can take that as my r. It's moving at a speed of 29 meters per second. The acceleration is equal to v squared divided by r. And if we calculate, we get an acceleration of 700 meters per second squared, which is kind of crazy. I mean, my assessment bells are going off and saying like, really? Is that possible? But this is a world-class athlete. Okay, it's a world-class athlete. So we're expecting kind of surprising numbers. So we'll postpone judgment for now. That just seems, so we're going to say that maybe perhaps that's reasonable. Okay, moving on. Next piece, we're going to continue our preparation by doing a free body diagram. And you have to think about the perspective that you use. Okay, we're going to do a problem with a car where we do a rear view of the car. But in the case of the hammer and the chain, it's best to do a top view. So here's the thing. The hammer is going in an arc of a circle like so. When it is right here, there's an acceleration which is directed towards the center of the circle. There is clearly a net force directed towards the center of the circle. And there's really one force that's acting, and it's the tension force. And that's it. Because the tension force, if it's accelerating at 700 meters per second squared, that's 70 Gs. So the force is 70 times, to make it do this, is 70 times larger than the weight force. We can pretty much ignore everything else. We can ignore drag. The tension force is the only game in town. So my free body diagram just looks like that. Now the net force, okay, is just going to be, let's take a look at my diagram here. So here's my arc of my circle. Hammer is going in a circle. Net force is directed towards the center. Tension force is directed towards the center. It's pretty clear that the net force is equal to the tension. But the net force is also equal to ma. So I can say the tension force is just equal to m times a. And the tension force is going to be equal to the mass, 7.3 kilograms, times the acceleration, which we said was 700 meters per second squared. If I calculate that, I get a force of 5,100 newtons. That's over 1,000 pounds, half a ton. Wow, which is kind of insane. And so my assessment, does this make sense, 5,100 newtons? It's a world-class thrower, and this is a pretty extreme event. If you watch people do it, it's kind of nuts. And he's holding on pretty hard, and he's putting a significant force with his legs. There's big forces involved here. And so my assessment, surprising, amazing, but probably legit. And this is the kind of circular motion problem that we're going to solve. Now let's do a quick aside here. Suppose I have a coin on a rotating turntable. At the time shown in the figure, which is the direction of the coin's velocity, we know that it's A. This is the way the coin is moving. Which is the direction of the frictional force on the coin? Well, there's got to be a force directed towards the center, and the only possible force is the force of static friction. Here's my question. Suppose the frictional force disappears. In which direction would the coin move? I want you to pause the video. I want you to think about that, and we'll come back. Well, the friction force is going to be equal to the net force on the coin, okay? So if the friction force goes away, if we said, okay, we just got rid of the friction force, this is no longer a thing. There is no net force, and if there's no net force, there is no acceleration. The velocity continues as it was, and the coin just moves in a straight line, okay? It's just going to keep moving in the direction it was headed. The friction force is making you make the turn. If the friction force goes away, you do not make the turn, you go in a straight line. And that brings us to this question, which is something we're going to solve on Friday. We're going to do that at our Friday synchronous session. And where this is saying this, if you have a car going down the road and it's making a sharp curve, okay, the force that makes the car turn the corner is friction, but friction can only be so large. And so the question asks basically, how fast can you go around this corner? Because if the friction force isn't big enough to make you make the turn, you don't make the turn, you go in a straight line, and that is a distinctly unhappy outcome that you do not want. This is a problem we'll look at this Friday. Next up in our slides, we're going to do a little bit more on circular motion. Here's my niece going down a slide, and of course what she's enjoying is the fact that as she's going down the slide, she does an arc of a circle and another arc of a circle. And she's enjoying the circular motion. Look at that joy on her face. Who doesn't love circular motion? And we'll do a little bit more of it in the next set of slides.